There are places on Earth where winter never truly ends, where temperatures plunge to -90 degrees Fahrenheit, where the sun disappears for months at a time, plunging entire regions into darkness, where the ground itself is frozen solid hundreds of feet deep. These are the coldest inhabited places on our planet. The Arctic, Siberia, Greenland, Alaska, northern Canada, Antarctica's research stations, regions so hostile that survival requires constant engineering intervention. Yet millions of people live there. Nations have staked claims. Industries extract resources worth trillions of dollars. Military bases project power across frozen wastes. This isn't simply about enduring cold. It's about nations that looked at the most inhospitable regions on Earth and decided they were worth conquering, worth inhabiting, worth transforming through engineering into strategic assets that shape global power. Over the next 3 hours, we'll explore how civilizations have pushed into these frozen frontiers, how ancient peoples first survived in the ice, how modern nations engineer entire cities where nothing should exist, how materials behave differently when frozen, how infrastructure must be redesigned from first principles, how the very act of building in extreme cold becomes a statement of national capability and ambition. We'll see how Russia maintains cities of hundreds of thousands in Siberia, where winter temperatures regularly hit -50. How Norway engineers oil platforms that operate in Arctic storms. How the United States built military installations across Alaska during the Cold War. How indigenous peoples developed technologies that allowed them to thrive for millennia before modern engineering arrived. This is about more than survival. It's about how nations extend their reach into places that should be uninhabitable. How engineering becomes a tool of territorial control. How the coldest places on Earth have become some of the most strategically important. This is how nations conquer ice. To understand the engineering challenge, you first need to understand what extreme cold does to everything it touches. Cold isn't just uncomfortable. It fundamentally changes how materials behave, how liquids flow, how machinery operates. At -40 degrees Fahrenheit, a temperature commonly experienced across the Arctic, steel becomes brittle. The metal that forms skyscrapers and bridges loses its flexibility. Under stress, instead of bending, it can shatter like glass. This isn't a minor inconvenience. It means every structural calculation must be rethought. Rubber hardens into useless rigidity. Tires crack. Seals fail. Hoses break. Materials engineers spend decades developing special compounds that remain flexible at temperatures that would destroy ordinary rubber. Concrete behaves unpredictably. Water trapped in its pores freezes and expands, creating internal stresses that crack the material from within. Standard concrete can disintegrate within a single winter cycle in Arctic conditions. Lubricants thicken or solidify completely. Motor oil becomes sludge. Hydraulic fluid refuses to flow. Machinery designed for temperate climates simply stops working when temperatures plunge far enough. Even air behaves differently. At extreme cold, it becomes denser, affecting everything from combustion efficiency to the lift generated by aircraft wings. Pilots flying in the Arctic must recalculate takeoff and landing procedures because standard performance charts don't apply. Water presents perhaps the greatest challenge. It freezes at 32 degrees Fahrenheit, but in Arctic regions, temperatures routinely drop 50 to 100 degrees below that threshold. Ice becomes harder than many types of stone. It accumulates weight that can collapse structures. It expands with enough force to burst pipes and crack foundations. But water's behavior creates another problem: permafrost. This is ground that remains frozen year-round, sometimes extending hundreds of feet deep. Building on permafrost requires entirely different engineering than building on normal soil. The ground seems solid, but it's actually ice-bonded soil that will turn to unstable mush if it thaws. These aren't problems that can be solved by simply making things stronger or adding insulation. They require fundamental reimagining of how construction works. Long before modern engineering, indigenous peoples developed sophisticated technologies that enabled survival in the Arctic. Their innovations weren't primitive substitutes for real engineering. They were elegant solutions to problems modern engineers still struggle with. The igloo represents one of humanity's most brilliant architectural achievements. Built entirely from snow and ice, materials most people consider the opposite of shelter, an igloo creates a warm, stable living space in the harshest environment on Earth. The engineering is remarkable. Snow blocks are cut in a specific size and shape, then arranged in a spiral that curves inward. Each block is carefully angled to transfer weight to the surrounding structure. The final keystone block locks everything together, creating a self-supporting dome that needs no internal framework. The shape itself is crucial. The dome distributes weight evenly, preventing collapse under heavy snow loads. Wind flows smoothly over the curved surface rather than creating destructive pressure points. The structure is strong enough that a person can stand on top without damaging it. But the thermal engineering is equally sophisticated. Snow is an excellent insulator because it traps air between ice crystals. The igloo's walls slow heat transfer from inside to outside. A single oil lamp or the body heat of occupants can raise interior temperature to a comfortable 60 degrees Fahrenheit even when outside temperature is -40. The Inuit carved a small entrance tunnel below floor level. This creates a cold trap. Cold air sinks and flows out while warm air rises and remains inside. This simple design maintains comfortable interior temperatures with minimal heat input. Sleds, clothing, and hunting equipment all reflected deep understanding of Arctic conditions. Fur clothing was designed in layers that trap air for insulation. Sealskin boots were waterproof yet breathable. Sleds were built with flexible joints that could flex over rough ice without breaking. These weren't people merely surviving despite the cold. They were people who understood the Arctic so thoroughly that they thrived there. Their technologies worked with the environment rather than fighting it, a principle modern engineers are only now fully appreciating. The Russian conquest of Siberia represents one of history's most ambitious territorial expansions. In less than a century, from the late 1500s to the 1600s, Russia expanded from the Ural Mountains to the Pacific Ocean, claiming territory larger than all of Western Europe. This wasn't expansion into fertile farmland or temperate forests. This was deliberate advancement into some of the coldest inhabited regions on Earth. Winter temperatures across much of Siberia drop below -40 degrees Fahrenheit. In parts of Yakutia, temperatures have been recorded below -90 degrees. The motivation was wealth, specifically fur. European and Asian markets paid enormous prices for Siberian sable, ermine, and fox pelts. Control of the fur trade meant control of extraordinary wealth. But extracting that wealth required establishing permanent settlements in conditions that killed unprepared settlers within days. Early Russian outposts were built using technology adapted from traditional log construction. Thick timber walls provided insulation. Steeply pitched roofs shed snow. Small windows minimized heat loss. Massive stone ovens called pesh dominated interior spaces, providing both heating and cooking capacity. These weren't simple structures. The logs were carefully selected, dried, and fitted together with precision joints that allowed thermal expansion and contraction without creating gaps. Moss was packed between logs for additional insulation. The construction techniques had been refined over centuries in Russia's cold interior regions, then adapted to even harsher Siberian conditions. The Russians learned from indigenous peoples, adopting some technologies while maintaining their own building traditions. They discovered which types of wood remained workable in extreme cold, which construction methods prevented ice accumulation, and how to position buildings to minimize wind exposure. Supply lines stretched thousands of miles. Everything from tools to food had to be transported across roadless wilderness. Rivers became highways during summer, frozen roads during winter. The logistics of maintaining settlements so far from established civilization required organizational capabilities that most nations lacked. But the settlements survived. They grew. Over centuries, they evolved from trading posts into towns, then cities. Today, Siberia hosts cities of hundreds of thousands of people, all living in conditions that would have seemed impossible to early explorers. Permafrost creates one of the most challenging engineering problems in polar regions. Understanding it requires thinking about ground in an entirely different way than engineers working in temperate climates. Permafrost is ground soil, rock, organic material that remains frozen for at least 2 consecutive years. In reality, much Arctic permafrost has been frozen for thousands of years. It can extend from just below the surface down hundreds or even thousands of feet. The top layer, called the active layer, thaws during summer and refreezes in winter. This layer might be only a few inches thick in the coldest regions or several feet thick in areas with warmer summers. Below this active layer lies the permanently frozen zone. The challenge is that permafrost only stays frozen if it remains cold. Sounds obvious, but the implications are profound. Any structure built directly on permafrost will transfer heat from its interior into the ground. This heat, over weeks and months, begins thawing the permafrost beneath the building. When permafrost thaws, the ice that was binding soil particles together melts. The ground loses strength and settles unevenly. Buildings tilt. Foundations crack. Structures can literally sink into the softening ground. In extreme cases, buildings collapse as the ground beneath them turns into an unstable slurry. Early Arctic construction often failed catastrophically because builders didn't understand this problem. They constructed buildings on what seemed like solid, frozen ground. For the first winter, everything seemed fine. Then as the building's heat gradually penetrated downward, the permafrost beneath began thawing. Within a few years, buildings tilted at dangerous angles or collapsed entirely. The solution requires preventing building heat from reaching permafrost. The most common approach uses pile foundations, essentially stilts that elevate the building above the ground. The piles are driven or drilled deep into permafrost, where they're held firmly by the frozen ground. Crucially, the space beneath the building remains open to outside air. Cold winter air circulates freely under the structure, keeping the ground frozen. The building's heat dissipates into the air rather than warming the ground. Some pile systems include thermosiphons, devices that actively remove heat from the ground. These work passively, using the temperature difference between air and ground to drive refrigerant circulation that extracts heat and dissipates it into the cold air. Norilsk, Russia, represents one of the most extreme examples of human habitation in cold climates. Located above the Arctic Circle in northern Siberia, it's home to 175,000 people living in conditions that challenge the limits of engineering and human endurance. Winter in Norilsk lasts 9 months. Temperatures regularly drop below -40 degrees Fahrenheit. The polar night, when the sun doesn't rise above the horizon, lasts from late November through mid-January. Yet this city, built almost entirely on permafrost, functions as a major industrial center. The reason Norilsk exists is mineral wealth. The region contains some of the world's richest deposits of nickel, copper, palladium, and platinum. Soviet planners decided this wealth was worth extracting regardless of the engineering challenges or human costs involved. The city was built largely by forced labor, prisoners of the Gulag system who constructed buildings, mines, and infrastructure under conditions that killed thousands. But what they built has endured for over 80 years, a testament to engineering adapted for extreme cold. Every building in Norilsk sits on pile foundations. The piles, driven deep into permafrost, support structures ranging from 5-story apartment blocks to massive industrial facilities. The space beneath buildings serves as storage and allows cold air circulation to preserve permafrost. Heating is centralized. Massive coal-fired power plants generate steam that's distributed through insulated underground pipes to buildings throughout the city. Individual buildings don't have separate heating systems. They're all connected to the citywide network. This centralized approach is more efficient in extreme cold than individual building heating would be. Water and sewage systems run through heated utility corridors above ground. In Norilsk's climate, underground pipes would freeze despite insulation. Instead, pipes are enclosed in heated structures that prevent freezing while remaining accessible for maintenance. The architecture is deliberately compact. Buildings are positioned close together to reduce wind exposure and create sheltered spaces between structures. Covered walkways connect many buildings, allowing residents to move around without exposing themselves to the worst weather. In northeastern Siberia lies Oymyakon, the coldest permanently inhabited place on Earth. The village has recorded temperatures as low as -96 degrees Fahrenheit. Yet approximately 500 people live there year-round, maintaining a community in conditions that would kill an exposed person within minutes. At these temperatures, Material behavior becomes extreme. Exposed skin freezes in seconds. Breath crystallizes into ice fog. Metal becomes so cold that touching it tears skin. Car tires can shatter. Fuel gels in tanks. Even the air seems to crack and snap. Yet people don't just survive. They maintain a functioning society. How is this possible? Construction in Oymyakon uses techniques developed over centuries. Buildings have walls up to 3 feet thick, using multiple layers of different materials. The innermost layer is often thick logs. Then insulation, historically moss or straw, now modern materials. Then an outer protective layer against wind and moisture. Windows are triple or quadruple glazed, with multiple air spaces between panes. Even so, frost accumulates on interior window surfaces during the coldest periods. Some traditional homes have shutters that close over windows at night, adding another insulation layer. Heating comes from massive wood-burning stoves that can weigh several tons. These aren't simple fires. They're sophisticated thermal mass heaters that burn wood efficiently, store heat in masonry, and radiate warmth for hours after the fire dies down. Yakutsk, the regional capital with nearly 300,000 residents, demonstrates how engineering adapts at urban scale. The entire city is built on permafrost. Every building uses pile foundations. But Yakutsk has developed techniques that go beyond simple elevation. Some piles include active cooling systems. Thermosiphons circulate refrigerant that extracts heat from the ground and dissipates it into the air. These systems actively preserve permafrost even when buildings above generate substantial heat. Water supply requires extraordinary measures. Water mains can't run underground, they'd freeze solid. Instead, they're installed in heated above-ground corridors called utilidors. These insulated passages contain not just water pipes but also sewage lines, electrical cables, and heating pipes. The utilidors are large enough for workers to enter for maintenance. They're heated just enough to prevent freezing, typically kept at 40 to 50 degrees Fahrenheit. Access points are positioned throughout the city for repairs and monitoring. In 1942, with World War II raging and fears of Japanese invasion of Alaska running high, the United States government made an extraordinary decision: build a 1,700-mile highway through the Canadian wilderness to Alaska in less than a year. The Alaska Highway Project required constructing a road through some of the most challenging terrain on Earth. Dense forests, endless swamps called muskeg, mountain ranges, rivers without bridges, and all of it frozen solid for much of the construction period. Over 11,000 U.S. Army troops and thousands of civilian contractors worked around the clock. The scale was staggering. At peak activity, new road was being completed at a rate of 8 miles per day. But the engineering challenges were unlike anything most workers had experienced. Muskeg presented a unique problem. This waterlogged ground, consisting of partially decayed vegetation, can be dozens of feet deep. In summer, it's impassable bog. In winter, it freezes solid on the surface but remains unstable underneath. Engineers discovered that simply scraping away the surface vegetation exposed the underlying muskeg to sun, causing it to thaw into an impassable swamp. The solution involved a technique called corduroy road, laying logs perpendicular to the road direction to create a stable surface that distributed weight. But in permafrost regions, the road construction itself created problems. Scraping away the surface vegetation and organic layer, which had insulated the permafrost, exposed it to summer warmth. The newly exposed permafrost began thawing, creating unstable road beds that undulated and cracked. Winter construction presented different challenges. Temperatures dropped below -60 degrees Fahrenheit. Equipment froze. Fuel gelled. Hydraulic lines burst. Soldiers slept in tents heated by wood stoves, often waking to find their blankets frozen to the tent walls from their own breath. Yet the highway was completed in 8 months, an engineering achievement that shocked even the project's planners. The original road was rough, subject to frequent washouts, and required constant maintenance. But it existed. It connected Alaska to the continental United States by land for the first time. Over subsequent decades, the highway was rebuilt and improved. Modern sections use sophisticated permafrost preservation techniques, including thermosiphons beneath the roadbed that actively extract heat, keeping the underlying ground frozen and stable. If the Alaska Highway connected Alaska to civilization, the Dalton Highway represents something different. Infrastructure designed specifically to enable resource extraction in the Arctic, regardless of engineering challenges. Built in 1974 to support construction and operation of the Trans-Alaska Pipeline, the Dalton Highway runs 414 miles from the interior of Alaska north to the Arctic Ocean. For much of its length, it's the only road within hundreds of miles. It crosses the Arctic Circle, traverses mountain ranges, and ends at Prudhoe Bay, one of the largest oil fields in North America. The highway is essentially a gravel road, unpaved along most of its length. This isn't cost-cutting, it's engineering necessity. Pavement creates a dark surface that absorbs solar heat. In permafrost regions, this heat transfer would thaw the underlying ground, destabilizing the road bed. Lighter-colored gravel reflects more heat, reducing permafrost thaw. The road bed itself requires sophisticated engineering. In many sections, thick insulation layers separate the road surface from underlying permafrost. These insulation boards slow heat transfer from summer sun to frozen ground beneath. Some sections use air ducts beneath the roadbed. Cold winter air flows through these ducts, actively cooling the ground. This preserves permafrost even in sections where the road surface experiences significant solar heating during summer. Culverts, drainage pipes under the road, must be carefully designed. They can't simply allow water to flow through. If not properly insulated and positioned, they create thermal shortcuts that transfer heat into permafrost, causing localized thawing and road collapse. Bridges present extreme challenges. In -40-degree temperatures, steel contracts. Expansion joints must accommodate this thermal movement. But the joints themselves can freeze, preventing movement and creating stress that can crack structural elements. The highway requires constant maintenance. Heavy truck traffic. It's primarily used by 18-wheelers hauling supplies to Prudhoe Bay and returning with nothing, creates potholes and ruts. Spring breakup, when surface layers thaw while deeper ground remains frozen, creates particularly difficult conditions. The road surface can turn into a muddy, unstable mess that traps vehicles. Yet the highway functions. It's remained operational for nearly 50 years, enabling billions of dollars in oil extraction from Arctic regions that would otherwise be inaccessible. The Trans-Alaska Pipeline represents one of the most ambitious engineering projects ever undertaken in Arctic conditions. The pipeline carries crude oil 800 miles from Prudhoe Bay on the Arctic coast to the ice-free port of Valdez in southern Alaska. The engineering challenges began with a fundamental problem. The oil pumped from underground emerges at approximately 145 degrees Fahrenheit. Running 800 miles of hot pipe across permafrost would create an environmental and structural disaster. The heat would thaw permafrost along the entire route, causing ground subsidence that would buckle and break the pipe. The solution required elevating much of the pipeline above ground. Along 420 miles of its route, more than half the total distance, the pipe sits on vertical supports that hold it several feet above the tundra. This elevation allows cold air to circulate beneath, preventing heat from reaching permafrost. But elevation created new problems. The pipe needed to accommodate enormous thermal expansion. As oil flows through, the pipe heats and lengthens. A straight pipe would buckle under this expansion. The solution was to design the elevated sections in a gentle zigzag pattern. As the pipe expands, the zigzags straighten slightly, accommodating the length change without creating destructive stress. The support structures themselves required innovation. Simple posts driven into permafrost would conduct heat downward from the pipe, eventually thawing the ground and losing stability. Engineers designed supports with thermosiphons, passive heat removal devices that extract heat from the ground. These thermosiphons are vertical pipes filled with refrigerant. When permafrost temperature rises above a certain point, refrigerant evaporates, rises to the top of the pipe, and is cooled by Arctic air. The cooled refrigerant condenses and flows back down, extracting more heat. The system works passively, requiring no power, using temperature differences to drive the cycle. Buried sections presented different challenges. In some areas, particularly crossing mountain ranges, elevation wasn't practical. The pipe had to go underground. but burying hot pipe in permafrost would cause thawing. The solution involved extensive insulation and, in some sections, refrigeration systems that actively cool the ground around the pipe. River crossings required suspending the pipe from bridges, or burying it beneath riverbeds at depths, where seasonal temperature changes wouldn't affect it. Each crossing needed custom engineering based on local conditions. Prudhoe Bay, located on Alaska's north slope along the Arctic Ocean, represents the northernmost major industrial facility in the United States. It's not a city in the conventional sense. It's an industrial complex where thousands of workers rotate through shifts, extracting oil from beneath the Arctic tundra. Winter temperatures regularly drop below -40 degrees Fahrenheit. The polar night lasts from late November through mid-January. Blizzards can shut down operations for days. Yet this facility has operated continuously since oil production began in 1977, producing billions of barrels of oil. Everything at Prudhoe Bay must be engineered for extreme cold. Drill rigs, processing facilities, storage tanks, pipelines, and support buildings all face conditions that would destroy equipment designed for temperate climates. The drilling rigs themselves require specialized components. Standard steel becomes brittle at Arctic temperatures. Critical structural elements use special low-temperature steel alloys that maintain flexibility at -60 degrees Fahrenheit. Hydraulic systems use specialized fluids that remain liquid in extreme cold. Processing facilities that separate oil, natural gas, and water from the crude mixture require massive heating systems. Chemical processes that occur naturally at moderate temperatures slow dramatically in cold. Heaters maintain process temperatures while the surrounding air is dozens of degrees below zero. Storage tanks for crude oil use heating coils to prevent the oil from gelling. Even with its viscosity reduced by being hot when pumped from underground, crude oil would thicken or solidify in unheated tanks during Arctic winter. Worker housing presents unique engineering challenges. Dormitories must provide comfortable living conditions while minimizing heat loss. Buildings use triple-pane windows, thick insulation, and vestibule entries that prevent cold air from entering main spaces when doors open. The entire complex sits on permafrost. Every structure uses pile foundations. Some buildings incorporate active cooling systems that preserve permafrost even when interior heating creates significant heat output. Waste management in Arctic conditions requires careful engineering. Sewage can't be dumped, environmental regulations are strict, and the ecosystem is fragile. Treatment facilities must process waste while maintaining operation in extreme cold, when biological processes slow dramatically. Greenland presents engineering challenges unlike anywhere else on Earth. The island is covered by an ice sheet up to 2 miles thick, containing enough frozen water to raise global sea levels by 24 feet if it melted completely. Only the coastal fringes are ice-free, and it's there that Greenland's 56,000 residents live. The capital, Nuuk, home to 18,000 people, represents the largest concentration of population. But calling it a city by continental standards would be misleading. There are no roads connecting Greenland's towns. They're too far apart, separated by fjords and glaciers. Travel between settlements occurs by boat in summer, snowmobile in winter, or by air year-round. Building in Greenland requires importing nearly everything. There are no forests, trees can't survive in the climate. Most lumber comes from Denmark or Canada. Concrete aggregates are quarried locally, but cement must be imported. Steel, glass, insulation, and mechanical systems all arrive by ship during the brief summer shipping season. Construction operates on tight schedules dictated by weather. The building season runs from roughly June through September. During these months, construction crews work extended hours to complete as much as possible before winter arrives. Foundations in Greenland's coastal areas often encounter bedrock close to the surface. This creates both advantages and challenges. Bedrock provides excellent bearing capacity, but drilling into frozen rock to install foundation anchors requires specialized equipment and considerable time. Many buildings use a hybrid foundation approach. Steel or concrete pads are anchored to bedrock. The building structure then connects to these pads, elevated slightly above ground level to prevent snow accumulation from creating ice dams against walls. Heating systems in Greenland have evolved over decades. Traditional buildings used imported fuel oil, which required expensive transport and created supply vulnerabilities. Modern buildings increasingly use electric heating powered by hydroelectric plants that harness meltwater from the ice sheet. These hydroelectric facilities represent engineering achievements in themselves. Dams and power plants must operate year-round despite conditions where water can freeze in pipes, ice accumulates on turbines, and access for maintenance becomes impossible during winter storms. Established in 1951 during the early Cold War, Thule served as a radar early warning station, positioned to detect Soviet bombers or missiles crossing the Arctic. The location was chosen precisely because of its proximity to the Soviet Union across the Arctic Ocean, despite, or perhaps because of, its extreme isolation. Building Thule required transporting hundreds of thousands of tons of equipment and materials to one of the most remote locations on Earth. During the initial construction in 1951–52, over 12,000 workers operated around the clock during the brief summer building season. Ships arrived with everything from bulldozers to entire buildings fabricated in sections. The base sits on permafrost. All structures use pile foundations, or are built on gravel pads that insulate the permafrost from building heat. The airfield, critical for the base's operation, required extensive engineering to create a stable runway surface that wouldn't develop frost heaves. Frost heaves occur when water in soil freezes and expands, pushing the ground's surface upward in irregular patterns. For aircraft runways, even minor frost heaves create dangerous conditions. The solution involved removing soil to substantial depth, replacing it with carefully graded gravel that drains well and doesn't hold water that could freeze and expand. The runway must be maintained year-round despite conditions that regularly drop below -40°F. Snow removal equipment operates continuously during winter storms. The runway surface is monitored constantly for ice accumulation, which is removed using specialized chemicals and mechanical equipment. Radar installations, the primary reason for Thule's existence, required engineering that maintained precise alignment despite extreme temperature swings. The radar antennas must remain accurately positioned to within fractions of a degree. Thermal expansion and contraction of supporting structures could throw calibration off. The solution involved mounting radar equipment on foundations that extend deep into permafrost, providing stability, while designing the above-ground structures to accommodate thermal movement without affecting radar alignment. Supporting a population of approximately 600 personnel year-round requires complete self-sufficiency. The base includes its own power plant, water treatment facility, waste processing maintenance shops, medical facilities, and housing. Everything must function regardless of outside conditions. Engineering for extreme cold requires understanding material behavior that textbooks for temperate climates never address. Every material behaves differently when frozen, and some differences are counterintuitive. Steel, the foundation of modern construction, becomes increasingly brittle as temperature drops. At room temperature, structural steel is ductile. It bends before breaking. This gives structures warning before failure and allows some deformation without catastrophic collapse. But at -40°F, many steel alloys lose this ductility. Under stress, instead of bending, they fracture suddenly. This brittleness was dramatically demonstrated by the sinking of the Titanic. The steel hull plates, already cold from North Atlantic water, shattered on impact with the iceberg rather than bending. Arctic construction uses special low-temperature steel alloys with altered chemical composition. These alloys maintain ductility at extreme cold, but they cost significantly more than standard steel. Engineers must calculate whether the additional cost is justified based on expected temperature ranges and structural requirements. Aluminum behaves differently than steel at low temperatures. Rather than becoming more brittle, aluminum actually becomes stronger while maintaining ductility. This makes it attractive for some Arctic applications. However, aluminum conducts heat much better than steel, creating thermal bridging problems where aluminum structural elements transfer heat or cold through building envelopes. Concrete's behavior in Arctic conditions depends critically on water content. Water trapped in concrete's pores freezes and expands, creating internal stresses. Multiple freeze-thaw cycles can reduce concrete to gravel over time. Arctic concrete uses special admixtures that reduce permeability, limiting how much water can penetrate the material. Air entraining agents create microscopic air bubbles throughout the concrete, providing space for ice expansion without creating destructive stress. The concrete must also be protected during curing. Concrete generates heat as it cures, a chemical reaction between cement and water. In temperate climates, this heat dissipates harmlessly. But in Arctic conditions, if the surface loses heat faster than the interior generates it, the concrete can freeze before fully curing, resulting in weak, crumbly material. Heating and insulating concrete during curing adds significant cost to Arctic construction. Temporary heated enclosures surround concrete pores, maintaining temperature above freezing for days or weeks until the concrete achieves sufficient strength. Svalbard, a Norwegian archipelago in the Arctic Ocean, sits between mainland Norway and the North Pole. At 78 degrees north latitude, it's one of the northernmost permanently inhabited places on Earth. Yet approximately 2,500 people live there year-round, maintaining a functioning society in conditions of extreme isolation and cold. The main settlement, Longyearbyen, began as a mining town. American John Longyear established coal mining operations in 1906, and the town grew around this industry. Norway assumed sovereignty in 1920, and mining continued for decades, shaping the community's character. Building in Svalbard required adaptations that went beyond even mainland Arctic construction. The permafrost here extends over 1,600 feet deep in places, among the deepest on Earth. Ground that has been frozen for millennia presents exceptional stability, but only if construction doesn't disturb the thermal equilibrium. Traditional Svalbard buildings use pile foundations drilled into permafrost. But the mining industry required different approaches. Mine tunnels extend horizontally into mountains, avoiding surface permafrost issues. The tunnels remain naturally cool year-round, and the surrounding rock provides structural support. These mining tunnels have found new purposes. The Svalbard Global Seed Vault, established in 2008, uses a decommissioned mine tunnel as humanity's backup storage for agricultural seeds. The tunnel's natural -3 degree Fahrenheit temperature, combined with additional cooling, preserves seeds potentially for centuries. The choice of Svalbard for this critical facility wasn't accidental. The extreme cold provides natural refrigeration. The remote location reduces risks from conflicts or disasters. The permafrost provides exceptional geological stability, and Norway's long-term political stability offers confidence in continued maintenance. Above ground, Longyearbyen's buildings reflect generations of Arctic construction experience. Structures are brightly colored, psychologically important during the polar night, when the sun doesn't rise from late October through mid-February. The colors also help buildings stand out during whiteout conditions. Utility systems follow Svalbard's unique terrain. Rather than burying utilities in permafrost, many pipes run above ground in insulated heated conduits. These utilidors are visible throughout the town, painted bright colors, creating a distinctive architectural character. The town is officially designated as a settlement rather than an incorporated municipality. This reflects its unusual status. It exists primarily to support mining and research activities rather than as a conventional community. Yet it has schools, shops, restaurants, and cultural facilities that create genuine community life. Antarctica represents the ultimate challenge for cold weather engineering. This isn't just another cold place. It's the coldest, driest, windiest continent on Earth. The lowest temperature ever recorded, -128.6 degrees Fahrenheit, occurred at the Soviet Vostok station in 1983. Unlike Arctic regions with indigenous populations who developed cold weather technologies over millennia, Antarctica had no permanent human presence until the 20th century. Every technique, every piece of equipment, every building had to be developed specifically for conditions beyond anything humans had previously inhabited. McMurdo Station, the largest Antarctic research facility, hosts over 1,000 people during summer and roughly 250 during winter. It's not a city or even a town. It's an industrial complex and research facility that exists solely to support scientific operations in the harshest environment on Earth. Construction in Antarctica faces challenges that go beyond even Arctic building. Materials must be shipped thousands of miles. The construction season is limited to the brief Antarctic summer, when temperatures might rise to a balmy 30 degrees Fahrenheit. Every component must be designed for assembly by workers wearing heavy cold weather gear. Buildings at McMurdo are modular structures, often prefabricated elsewhere and assembled on-site. This reduces construction time and minimizes exposure to extreme conditions. The modules are connected to form larger facilities, with covered passages between buildings reducing outdoor exposure. The station sits on volcanic rock rather than permafrost, which simplifies foundation work, but presents its own challenges. The rock is extremely hard, requiring specialized equipment for excavation. Anchoring structures against winds that can exceed 100 miles per hour requires deep, securely fastened foundations. Heating systems consume enormous amounts of fuel. McMurdo burns over 5 million gallons of petroleum annually just for heating and power generation. All of this fuel must be shipped in during the brief summer shipping season and stored in massive tanks. Water is actually scarce in Antarctica despite being surrounded by ice. The continent receives almost no precipitation. It's technically a desert. Water for McMurdo comes from a desalination plant that processes seawater. The plant must operate continuously, as water storage capacity is limited, and the consequences of water system failure in winter would be catastrophic. Waste management presents unique challenges. Nothing can be discarded onto the ice. International treaties require that all waste be removed from the continent. Trash is sorted, compacted, and stored until ships arrive to transport it away. Sewage undergoes treatment before any discharge. The Amundsen-Scott South Pole Station represents perhaps the most extreme permanent human habitation on Earth. Located at the geographic South Pole, it experiences 6 months of continuous daylight followed by 6 months of continuous darkness. Winter temperatures average -76 degrees Fahrenheit, occasionally dropping below -100. The station must be completely self-sufficient during winter, when no aircraft can land or take off due to extreme cold. The skeleton crew of roughly 50 winter personnel must survive without resupply or possibility of evacuation for approximately 8 months. The current station, completed in 2008, replaced an earlier facility that was literally being crushed by accumulating ice. The South Pole sits on an ice sheet over 9,000 feet thick that's constantly moving and accumulating more ice through snowfall. Any structure built on this ice will eventually be buried. The solution was extraordinary. Build a station that can be raised as snow accumulates beneath it. The building sits on hydraulic jacks mounted on stilts driven into the ice. As snow accumulates, the building can be jacked up several feet, and the stilts extended. This process can be repeated multiple times before the building needs replacement. The structure's shape is aerodynamic, designed to minimize snow accumulation on the windward side, while encouraging snow deposition on the leeward side. This creates a kind of self-leveling effect, reducing the rate at which the building becomes buried. Inside, the station includes everything needed for long-term habitation: dormitories, dining facilities, laboratories, communications equipment, power generation, water production, and medical facilities. The entire complex is interconnected, allowing residents to move throughout without venturing outside. The station generates its own electricity using jet fuel generators. Fuel consumption is enormous. The station burns roughly 65,000 gallons during the winter months, when temperatures drop so low that machinery requires nearly constant operation to prevent freezing. Water comes from a unique system. A heated probe melts ice in a chamber called a Rodriguez well, named after its inventor. The probe melts ice faster than the meltwater refreezes, creating a reservoir of liquid water that's pumped to the surface. The system requires constant energy input, but provides reliable water in an environment where nothing liquid exists naturally. The station's elevation, 9,300 feet above sea level, creates additional challenges. The altitude effect is amplified by the extremely cold, dense air. The physiological altitude is roughly equivalent to 11,000 feet at lower latitudes. Newcomers often experience altitude sickness, and even acclimated residents operate at reduced physical capacity. Accessing Arctic regions requires ships capable of breaking through sea ice meters thick. Icebreakers represent specialized engineering that allows maritime access to regions that would otherwise be unreachable for much of the year. The most powerful icebreakers are Russia's nuclear-powered Antarctica-class vessels. These ships can break through ice over 9 feet thick, maintaining steady progress through pack ice that would stop conventional vessels completely. The hull design is critical. Icebreakers don't simply smash through ice, they ride up onto it, using the ship's weight to break downward through the ice sheet. The bow is specially shaped and reinforced to enable this process without damaging the hull. The hull plating is much thicker than standard ships, up to 2 inches of special steel in the ice contact zones. The steel itself is formulated to resist brittle fracture at extreme cold. Standard ship steel can shatter if stressed when frozen, but icebreaker steel maintains ductility at -40 degrees Fahrenheit. The propulsion system must generate enormous power. The Antarctica-class icebreakers produce 75,000 horsepower, roughly equivalent to 500 automobile engines. This power is needed to drive the ship up onto ice, break through, and maintain forward progress against the massive resistance of fractured ice pieces. The nuclear reactors that power these ships provide advantages beyond just raw power. They eliminate the need for fuel storage and refueling, allowing extended operations without port visits. The Antarctica-class vessels can operate for 3 to 4 years without refueling, cruising over 100,000 miles. But nuclear power creates its own challenges. The reactors must be shielded and maintained even in extreme cold. Cooling systems must function when seawater is near freezing. Emergency systems must operate regardless of outside temperature. The ships also incorporate ice clearing systems. Water jets along the hull spray seawater forward onto the ice, creating a lubricating layer that reduces friction. Air bubble systems create channels of air beneath the hull, further reducing friction and improving icebreaking efficiency. Living conditions aboard icebreakers require special consideration. Crews may spend weeks or months in Arctic conditions. The ships include heated living quarters, recreational facilities, and systems to maintain comfortable humidity despite extremely cold outside air. Extracting oil and gas from beneath Arctic seas presents engineering challenges that combine offshore platform design with ice-resistant construction. These platforms must withstand forces from storms, waves, and uniquely moving ice sheets. The Pryorozlomnia platform in the Russian Arctic represents one approach. This gravity-based structure sits on the seafloor, held in place by its own weight rather than anchored with piles. The base is designed to resist ice loads that would destroy conventional platforms. The platform's shape is critical. Rather than vertical walls that ice could crush, the structure has sloped sides. When ice sheets moving with currents encounter the platform, they ride up the slope and break. This redirects the ice's energy upward rather than horizontally against the structure. The forces involved are staggering. Arctic ice sheets can be several feet thick and driven by currents and winds. The impact force when such ice hits a structure can exceed thousands of tons. Platform designs must account for these extreme loads while maintaining stability in water depths of 60 to 200 feet. Materials for Arctic platforms must perform in seawater at temperatures near or below freezing. Steel exposed to cold seawater and salt spray corrodes differently than in temperate oceans. Special coatings and cathodic protection systems prevent corrosion that could weaken critical structural elements. The platform's topside facilities, drill rigs, processing equipment, worker quarters, must function in conditions similar to land-based Arctic operations, but with the added challenge of being at sea. Heating systems must provide warmth while withstanding corrosive salt spray. Helicopter landing pads must remain ice-free for emergency evacuations. Worker rotation follows strict schedules. Personnel typically work shifts of several weeks on the platform, followed by time off on shore. This reduces the psychological stress of isolation, while ensuring experienced crews operate critical systems. Some platforms use artificial islands created by piling rock and gravel on the seafloor. These islands rise above sea level, providing a stable work platform. The island itself is engineered to resist ice forces, with sloped sides that break up ice sheets before they can exert destructive horizontal pressure. Emergency systems on Arctic platforms are designed with redundancy that would seem excessive elsewhere. Multiple backup power systems, duplicate heating equipment, and extensive safety equipment reflect the reality that rescue in Arctic conditions can be delayed for days during severe weather. Communication systems must function when ice accumulation on antennas could disrupt signals. Heating elements keep critical equipment ice-free. Satellite communications provide backup when conventional radio systems fail. The platforms also include environmental protection systems beyond what's required in temperate waters. Oil spill containment in ice-covered seas requires specialized equipment. Booms that contain spills in open water don't work when ice is present. Recovery systems must handle oil mixed with ice and snow. The Northern Sea Route, running along Russia's Arctic coast from the Atlantic to the Pacific, represents one of the most ambitious maritime transportation corridors ever developed. For much of history, it was impassable, locked in ice for most of the year, navigable only by the most powerful icebreakers. The route offers enormous advantages. It cuts roughly 40% off the distance between Europe and Asia, compared to the traditional route through the Suez Canal. For shipping companies, this means significant fuel savings and faster delivery times. But it requires navigating some of the most challenging waters on Earth. The route is ice-covered for 8 to 10 months per year across much of its length. Even during the brief summer window when ice retreats, the passage requires icebreaker escort for most vessels. Russia maintains a fleet of nuclear and diesel-powered icebreakers specifically to enable commercial traffic. Ships using the route must meet strict ice class requirements, construction standards that ensure hulls can withstand ice impacts. Ice-strengthened hulls use thicker steel plating, reinforced frames, and special bow designs that help break through ice rather than being crushed by it. Navigation in ice requires skills beyond normal maritime operations. Ice charts are consulted constantly, showing ice thickness, movement, and concentration. Captains must decide when to push through ice, when to wait for ice movement to create leads, channels of open water, and when conditions are too dangerous to proceed. The Russian government has invested heavily in Arctic infrastructure, supporting the Northern Sea Route. New ports capable of handling large vessels have been built along the coast. Search and rescue stations are positioned at intervals. Emergency supply depots stock fuel, food, and spare parts. Satellite systems specifically monitor the route, providing real-time ice data, weather information, and vessel tracking. This coordination is essential. Ships trapped in ice need rapid assistance before fuel runs out or hull damage occurs. Climate change is altering the Northern Sea Route's viability. Ice extent and thickness have decreased over recent decades, extending the navigable season and making some sections passable without icebreaker escort. This has increased traffic dramatically, from a handful of transits annually a few decades ago to dozens now. But this increased accessibility creates new challenges. More ships mean greater risk of accidents, oil spills, or environmental damage in fragile Arctic ecosystems. Search and rescue capabilities must expand to cover increased traffic. Regulatory frameworks are still developing for this emerging transportation corridor. Permafrost, which has provided stable foundations for Arctic construction for decades, is now becoming a source of engineering crisis. Climate warming is causing permafrost to thaw at unprecedented rates, destabilizing buildings, roads, pipelines, and other infrastructure built assuming permanently frozen ground. The problem manifests in multiple ways. Buildings that have stood for 50 years suddenly begin tilting as permafrost beneath their foundations thaws. Foundations that were driven into frozen ground find themselves surrounded by mud. The ground surface settles unevenly, creating depressions and cracks. Roads built across permafrost develop waves and holes as the ground beneath them thaws at different rates. What was a smooth surface becomes dangerously rutted. In severe cases, sections of road simply collapse into thermokarst, sinkholes created when ground ice melts. Pipelines face particular risk. Sections that were stable for decades can suddenly sag or buckle as supporting ground thaws. For pipelines carrying oil or gas, this creates potential for ruptures and catastrophic spills in environmentally sensitive Arctic regions. Engineers are developing multiple approaches to address thawing permafrost. Some involve active intervention, refrigeration systems that cool the ground artificially, maintaining frozen conditions even as air temperatures warm. These systems require substantial energy input, making them expensive to operate long-term. Other approaches focus on adapting foundations to remain stable even if permafrost thaws. Adjustable pile systems allow buildings to be re-leveled as ground conditions change. Some new construction uses foundation designs that don't depend on frozen ground, instead anchoring to bedrock below the permafrost layer. In some cases, infrastructure is being relocated away from areas where permafrost thaw is most severe. This is expensive and disruptive, but in regions where permafrost is degrading rapidly, it may be the only viable long-term solution. The challenge extends to entire cities. Norilsk, Yakutsk, and other major Siberian cities built entirely on permafrost face the prospect of widespread foundation failures. Billions of dollars in infrastructure could be at risk. Government agencies and engineering firms are conducting comprehensive surveys to assess vulnerability and prioritize interventions. This represents an unexpected consequence of building in permafrost regions. The engineering solutions worked brilliantly for decades, but they depended on one critical assumption: that the ground would remain frozen. As that assumption fails, the engineering must adapt, often at enormous cost. While Siberia and the Arctic represent extreme cold, Finland and Scandinavia demonstrate how engineering enables not just survival but comfortable, modern urban life in sustained winter conditions. Helsinki experiences average January temperatures around 25 degrees Fahrenheit, not as extreme as Siberian cities, but cold enough that snow cover lasts months and winter dominates much of the year. Yet Helsinki functions as a vibrant, modern city where winter is integrated into urban life rather than something to merely endure. The engineering begins with urban planning. Finnish cities are designed assuming snow and ice will be present for much of the year. Streets are planned with snow removal in mind, wide enough for plows to operate efficiently, with designated snow storage areas where removed snow is piled. District heating systems, developed in Scandinavia and now used worldwide, originated partly to address winter energy demands efficiently. Rather than each building having its own heating system, centralized plants generate heat that's distributed through insulated underground pipes to buildings throughout the city. This approach offers multiple advantages. Large central plants achieve better efficiency than individual building systems. They can use various fuel sources, including waste incineration and industrial waste heat. The distribution system is insulated and maintained professionally, reducing heat loss. Buildings themselves are engineered for energy efficiency, while maintaining comfort. Triple-glazed windows are standard. Wall insulation far exceeds requirements in warmer climates. Ventilation systems include heat recovery, extracting heat from outgoing air to warm incoming fresh air. Transportation infrastructure operates reliably through winter. Helsinki's metro system runs partially underground, protected from snow and ice. Above-ground sections use heated switches and sophisticated snow removal systems. Trains run on schedule regardless of weather. The city maintains an extensive network of heated sidewalks and bike paths. Electric heating elements beneath pavement surfaces keep key pedestrian and cycling routes ice-free. This infrastructure investment reflects a philosophy that winter shouldn't prevent walking and cycling. Snow management is a massive logistical operation. Helsinki removes approximately 1 million cubic meters of snow annually, enough to fill 400 Olympic swimming pools. The snow is transported to designated dumping areas, often industrial sites or waterfronts where spring melting won't cause flooding problems. Public spaces are designed to remain usable year-round. Parks include winter lighting and cleared paths. Ice skating rinks are maintained in multiple locations. Winter festivals and activities make cold months culturally vibrant rather than something to wait out indoors. Murmansk, located on Russia's northwestern coast above the Arctic Circle, is the world's largest city north of the Arctic Circle, with a population of approximately 270,000. Despite its extreme northern latitude, 68 degrees north, it maintains a major seaport that remains ice-free year-round. The port's ice-free status results from the North Atlantic Current, an extension of the Gulf Stream that brings relatively warm water north along the Norwegian coast. This geological accident has strategic implications. Murmansk provides Russia with year-round naval access to the Atlantic Ocean, unlike ports in the Baltic or Arctic regions that freeze in winter. The city's existence reflects strategic priorities overriding environmental challenges. Murmansk was founded in 1916 specifically to provide an ice-free port for receiving Allied supplies during World War I. The city has maintained strategic importance ever since, particularly as a naval base for Russia's Northern Fleet. Building a city of this size in Arctic conditions required massive construction efforts. Like other Arctic cities, Murmansk is built largely on permafrost. Every building uses pile foundations. District heating from centralized power plants provides warmth to residential and commercial buildings throughout the city. The polar night lasts from early December through mid-January, 40 consecutive days when the sun doesn't rise above the horizon. Conversely, the midnight sun lasts from mid-May through late July. These extreme light cycles affect not just engineering but psychology and social organization. Street lighting in Murmansk is extensive, combating winter darkness. Buildings use bright colors, vibrant yellows, blues, and reds, providing visual stimulation during dark months. Public spaces include artificial lighting designed to provide some approximation of daylight during the polar night. The port facilities themselves represent sophisticated Arctic engineering. Docks and piers must withstand ice forces, even though the harbor doesn't fully freeze. Floating ice from other areas can enter the port, requiring structures that can resist ice impacts. Loading equipment must function in temperatures that regularly drop below 0 Fahrenheit. Ship repair facilities must operate year-round, which means working on vessels in extreme cold. Dry docks require heating systems that keep working areas comfortable while ships undergo maintenance. Welding, painting, and mechanical work all face challenges from cold that slow chemical processes and affect material properties. Iceland presents a unique case, a subarctic island nation that has harnessed volcanic geology to create engineering solutions unavailable anywhere else in the Arctic. Despite its northern latitude, the island lies just south of the Arctic Circle. Iceland's climate is moderated by the Gulf Stream, but winters are still cold, windy, and dark. Early Icelandic settlers faced significant survival challenges, constructing turf houses partially underground for insulation. Modern Iceland has transformed itself through geothermal engineering. The island sits on the mid-Atlantic ridge, where tectonic plates are pulling apart, creating volcanic activity and geothermal heat close to the surface. Iceland has systematically tapped this heat for power generation and district heating. Approximately 90% of Icelandic homes are heated with geothermal energy. Hot water from underground is pumped to the surface, piped to towns and cities, and distributed through buildings. In Reykjavik, the capital, virtually every building connects to the geothermal heating network. The infrastructure required is substantial. Wells are drilled to depths of 6,000 feet or more, accessing water heated to 300 to 400 degrees Fahrenheit by underground volcanic heat. The water is brought to the surface through insulated pipes. Because the water is often mineralized and corrosive, many systems use heat exchangers. The geothermal water heats clean water in a closed-loop system, which is then distributed to buildings. This prevents corrosive minerals from damaging building heating systems. The same geothermal resources generate electricity. Iceland produces virtually all its electricity from renewable sources, roughly 75% hydroelectric and 25% geothermal. This abundant, cheap electricity has attracted energy-intensive industries like aluminum smelting. Geothermal heat has enabled innovations impractical elsewhere. Sidewalks and streets in Reykjavik use geothermal heating to remain ice-free in winter. The city's main shopping street, Laugavegur, is snow-free year-round despite Iceland's climate. Greenhouses heated by geothermal energy produce vegetables and even tropical fruits year-round in Iceland. This seems impossible, growing bananas just south of the Arctic Circle. But geothermal heat makes it economically viable. The Blue Lagoon, originally a byproduct of geothermal power generation, demonstrates creative use of thermal water. The lagoon is fed by discharge water from a geothermal power plant, maintaining temperatures around 100 degrees Fahrenheit year-round. It's become a major tourist attraction, generating revenue from what was originally considered waste. Military operations in Arctic conditions require engineering that goes beyond civilian cold weather construction. Equipment must not just function, but perform tactically in conditions that would disable conventional military hardware. Tanks and armored vehicles face multiple challenges in extreme cold. Engine oil thickens, making cold starts difficult or impossible without preheating. Batteries lose capacity. A battery that works fine at 70 degrees Fahrenheit might provide only 40% of its power at -20. Military engineers develop solutions including engine block heaters, battery warming systems, and special lubricants that remain fluid at extreme cold. Some vehicles include auxiliary power units that can run continuously during cold weather, providing heat to keep the main engine ready for immediate start. Track systems on armored vehicles must use special rubber compounds that don't become brittle and crack in cold. Metal tracks can become so cold that they cause frostbite on contact, requiring soldiers to wear insulated gloves when performing maintenance. Weapons systems face their own challenges. Standard firearms can malfunction when lubricants freeze. Arctic weapons use dry lubricants or specially formulated oils. Ammunition must be stored carefully. Powder charges can be affected by extreme cold, altering ballistic performance. Optical systems frost over or develop condensation when brought from cold exterior air into heated spaces. Military optics include anti-fog coatings and heating elements. Night vision devices must be specially designed for Arctic conditions where temperature gradients affect infrared imaging. Shelter systems for Arctic military operations have evolved from tents to sophisticated modular structures. Modern systems include insulated panels that interlock to create heated shelters rapidly. The shelters can withstand high winds and heavy snow loads while providing enough insulation that a small heater maintains comfortable interior temperature. Communication equipment must function when batteries fail rapidly and antennas accumulate ice. Military radio systems include cold weather battery packs with greater capacity and chemical hand warmers that can be inserted into battery compartments for emergency power maintenance. The U.S. military maintains specialized Arctic warfare training centers where soldiers learn cold weather survival, equipment operation, and tactical procedures. These facilities replicate extreme cold conditions, training personnel before deploying to actual Arctic environments. In mountain regions where snow accumulates to great depths, avalanche engineering becomes critical for protecting infrastructure and populations. This specialized field combines understanding snow physics with structural engineering and terrain management. Snow behaves as a material unlike anything else engineers typically encounter. It can range from light, fluffy powder to dense, hard slabs. It bonds to itself and underlying surfaces in complex ways. It undergoes continuous transformation after falling, with temperature, pressure, and time changing its properties. Avalanche formation occurs when accumulated snow loses stability and slides down a slope. The triggers can be additional snowfall adding weight, temperature changes affecting snow bonding, or mechanical disturbances like earthquakes or human activity. Once moving, avalanches can reach speeds exceeding 80 miles per hour, carrying thousands of tons of snow. The impact forces can destroy buildings, sweep away vehicles, and bury infrastructure under debris dozens of feet deep. Switzerland, with extensive alpine territory and major transportation routes through avalanche-prone areas, pioneered avalanche engineering. The country has developed comprehensive systems to protect railways, highways, and settlements. Passive protection structures include avalanche barriers positioned on slopes above infrastructure. These are typically steel or concrete structures designed to hold snow in place, preventing avalanche formation. The barriers must withstand enormous forces, the weight of deep snow plus wind and temperature stresses. Deflection structures redirect avalanches away from protected areas. V-shaped wedges can split avalanche flows, guiding them around buildings or infrastructure. Deflection dams channel avalanches into designated runout zones where they can dissipate harmlessly. Snow sheds, also called avalanche galleries, cover roads or railways in avalanche paths. These are essentially tunnels with heavily reinforced roofs designed to let avalanches pass over while protecting traffic below. The Swiss railway system includes miles of snow sheds protecting critical mountain routes. Active avalanche control involves deliberately triggering avalanches under controlled conditions before they can become dangerous. Artillery, explosives lowered from helicopters, or permanent explosive systems can trigger releases of accumulated snow before it becomes unstable enough to avalanche spontaneously. Modern avalanche forecasting uses weather data, snowpack analysis, and computer modeling to predict avalanche risk. This allows closing roads or railways preventively and scheduling controlled releases for optimal timing. Canada's approach to winter cities demonstrates different philosophies than Scandinavian models. Rather than embracing winter outdoor activities, Canadian cities like Montreal and Toronto have built extensive underground and enclosed systems that allow avoiding harsh weather entirely. Montreal's underground city, officially RSO, represents the world's largest underground pedestrian network. Over 20 miles of passages connect metro stations, office buildings, hotels, shopping centers, and residential buildings. Approximately 500,000 people use the system daily, particularly during winter. The engineering challenge involved coordinating hundreds of separate developments over decades. Each building owner had to agree to connect, maintain common standards, and allow public access through private property. The result is a network that emerged organically rather than through centralized planning. The passages must handle enormous pedestrian volumes during rush hours. Ventilation systems provide fresh air to spaces that would otherwise be stuffy and uncomfortable. Climate control maintains year-round comfort. Cool in summer when Montreal can reach 90 degrees Fahrenheit. Warm in winter when temperatures drop below zero. Emergency systems include multiple evacuation routes, fire suppression systems, and emergency lighting. Because the passages connect so many buildings, fire safety requires coordination across properties and jurisdictions. Above ground, Montreal addresses winter through aggressive snow removal. The city operates one of the world's most sophisticated snow management systems, removing approximately 9 million cubic meters of snow annually from streets, sidewalks, and public spaces. Snow removal isn't just plowing, it involves actually removing snow from the city. Trucks load snow from cleared streets and transport it to designated snow dumps, often industrial areas or sites where spring melting won't cause flooding or infrastructure damage. The city maintains over 2,000 pieces of snow removal equipment, including specialized sidewalk plows, snow blowers, and front-end loaders. Operations run 24/7 during snowfall, with shifts of workers ensuring streets remain passable even during major storms. Quebec City takes a different approach, embracing winter through architecture and planning that makes cold months attractive rather than something to escape. The Winter Carnival, ice sculptures, and winter sports integrate cold weather into cultural identity. Fairbanks, Alaska, represents the largest American city experiencing true continental Arctic climate. Located in Alaska's interior, far from oceanic moderating influences, Fairbanks regularly sees winter temperatures drop below -40 degrees Fahrenheit. The record low is -66. The city's 32,000 residents have developed engineering solutions to challenges that most Americans never experience. Ice fog, a phenomenon where water vapor freezes into tiny ice crystals suspended in air, creates unique problems during the coldest periods. Ice fog forms when moisture from vehicle exhaust, building heating systems, and even human breath meets extremely cold air. The water vapor instantly freezes into ice crystals that hang suspended, reducing visibility sometimes to a few dozen feet. Driving becomes hazardous. Aircraft can't land or take off safely. Building design in Fairbanks must account for temperature extremes ranging from -60 to +90 degrees Fahrenheit, a range of 150 degrees. This thermal cycling creates stresses that would destroy buildings designed for temperate climates. Foundations use various approaches depending on local soil conditions. Some areas have permafrost, requiring pile foundations. Other areas have soils that freeze and thaw seasonally, requiring different foundation designs that can tolerate frost heaves and settling. Vehicle engine block heaters are essential. Parking lots include electrical outlets where drivers can plug in heaters that keep engine blocks warm enough for cold starts. Without this heating, engines simply won't start after sitting in -40-degree cold. The electrical infrastructure to support thousands of engine block heaters is substantial. Parking areas must be wired with adequate capacity, and the electrical load during extreme cold spikes significantly as everyone plugs in their vehicles. Water and sewer systems require careful engineering. Most systems run in insulated utilidors, above ground or just below surface passages that provide some heating. Completely underground systems without heating would freeze solid within hours during winter cold snaps. The University of Alaska Fairbanks maintains extensive cold weather research facilities, testing everything from building materials to fuel formulations to clothing systems. This research benefits not just Fairbanks but cold climate engineering worldwide. Arctic engineering stands at an inflection point. Climate change is altering the physical conditions that have defined cold region engineering for decades. Simultaneously, new technologies are enabling approaches that were impossible previously. Advanced materials are transforming what's possible. Aerogel insulation, with thermal performance far exceeding conventional materials, allows thinner walls with better insulation. Carbon fiber composites maintain strength at extreme temperatures while being much lighter than steel. Phase change materials can store and release thermal energy, potentially revolutionizing building heating. These materials absorb heat when warm and release it when cold, passively moderating temperature swings. Integrated into building structures, they could reduce heating energy requirements substantially. Renewable energy systems designed specifically for Arctic conditions are advancing. Solar panels that function in low-angle sunlight and extreme cold, wind turbines with de-icing systems, and systems that generate power from temperature differentials between air and ground are all under development. 3D printing technology could transform Arctic construction. Rather than shipping materials and equipment thousands of miles, future construction might use local materials, even ice and snow, processed through advanced 3D printing systems. Research has demonstrated that ice structures created through 3D printing can achieve remarkable strength. Autonomous systems for infrastructure monitoring and maintenance are becoming practical. Drones can inspect pipelines, transmission lines, and building exteriors more safely and efficiently than human workers in extreme cold. Robotic systems can perform some maintenance tasks without exposing humans to dangerous conditions. Artificial intelligence is being applied to building energy management, optimizing heating based on weather forecasts, occupancy patterns, and energy costs. These systems can reduce energy consumption while maintaining comfort. The changing Arctic climate itself is altering engineering requirements. Permafrost thaw means foundations designed for frozen ground must be rethought. Extended ice-free seasons in Arctic waters change requirements for marine infrastructure. Altered snow and ice patterns affect avalanche engineering and winter road maintenance. Some projections suggest Arctic regions could become more habitable and economically valuable as global temperatures rise. This could drive increased construction and development. But this development must account for unstable transition conditions. Permafrost thawing unpredictably, changing precipitation patterns, and other shifts that create engineering uncertainties. The Arctic is becoming a focal point for international competition, as melting ice reveals access to vast natural resources and new shipping routes. Engineering capabilities increasingly determine which nations can effectively project power and extract value from Arctic regions. Geological surveys suggest the Arctic may contain 13% of the world's undiscovered oil reserves and 30% of undiscovered natural gas. Mineral deposits including rare earth elements, gold, and diamonds exist in commercial quantities. But accessing these resources requires engineering capabilities that only a handful of nations possess. Russia has invested most heavily in Arctic engineering infrastructure. With over half of Arctic coastline and extensive Siberian territories, Russia views Arctic development as central to national interests. The country maintains dozens of Arctic military bases, operates the world's largest icebreaker fleet, and continues building Arctic-capable infrastructure. The United States, primarily through Alaska, maintains significant Arctic presence, but has invested less in recent decades than Russia. American icebreaker capacity has declined while Russian and Chinese capabilities have expanded. This creates strategic vulnerabilities as Arctic shipping routes become more accessible. China, despite having no Arctic territory, has declared itself a near-Arctic state and invested heavily in Arctic research, resource development partnerships, and icebreaker construction. Chinese engineering firms are developing capabilities for Arctic construction and resource extraction. Norway has positioned itself as a leader in Arctic offshore engineering, developing technologies for oil and gas extraction in ice-prone waters. Norwegian companies have built some of the world's most sophisticated Arctic-capable drilling platforms and support vessels. Canada's vast Arctic territories include significant resource potential, but development has been limited by environmental concerns, indigenous land rights, and the enormous costs of Arctic infrastructure. Canadian engineering capabilities in permafrost construction and cold weather operations are well developed but applied selectively. Territorial disputes add political complexity to Arctic engineering. Russia's claim to extended continental shelf under the Arctic Ocean, potentially rich in resources, conflicts with claims from Denmark through Greenland, Canada, and Norway. These disputes create uncertainty about jurisdictions and development rights. The Ilulissat Declaration of 2008, signed by Arctic nations, committed to resolving disputes through existing international law. But as resources become more accessible and valuable, the engineering challenges of Arctic operations become entangled with geopolitics. Military considerations increasingly drive Arctic engineering. Russia has rebuilt Soviet-era Arctic military bases and constructed new facilities. The United States has increased military exercises in Alaska and Arctic waters. NATO allies conduct cold weather training in Norway and Iceland. Engineering in Arctic regions must increasingly account for environmental impacts on ecosystems that are both fragile and slow to recover from disturbance. Arctic tundra takes decades or centuries to recover from physical damage. Vehicle tracks across tundra can remain visible for 50 years. Disturbed permafrost can trigger thermokarst formation that expands over time. These realities require engineering approaches that minimize ecosystem disturbance. Modern Arctic construction uses strict environmental protocols. In many regions, construction equipment must operate only when ground is frozen and snow-covered, preventing damage to underlying vegetation and soil. Summer construction, when ground is exposed, requires using established roads and work areas. Waste management in Arctic environments presents unique challenges. Biological processes that break down waste in temperate climates slow dramatically in cold. Organic waste can remain preserved for years in permafrost. Arctic facilities must either process waste to completion or remove it entirely rather than relying on natural decomposition. Oil spill response in Arctic conditions requires specialized engineering. Oil behaves differently when cold. Some petroleum products become thick and gel-like. Others remain fluid but are harder to detect under ice. Conventional boom containment systems don't work when ice is present. Response equipment must function in conditions where chemical dispersants may not work effectively. Arctic engineering increasingly incorporates environmental monitoring as a design feature. Structures include sensors that detect changes in permafrost temperature, ground settlement, or water chemistry. This data allows early detection of environmental impacts and enables adaptive management. Some projects incorporate environmental protection into core design. Elevated pipelines allow wildlife migration beneath. Platforms are positioned to avoid critical habitats. Construction timing is scheduled around breeding or migration seasons. Indigenous communities, who have inhabited Arctic regions for millennia, are increasingly involved in engineering decisions affecting their territories. Traditional ecological knowledge complements scientific understanding, providing insights into ice conditions, animal behavior, and environmental changes that inform better engineering decisions. The principle of environmental engineering in the Arctic has evolved from simply minimizing damage to actively designing for ecosystem compatibility. This adds cost and complexity, but reflects recognition that Arctic environments cannot be treated as empty frontiers to be exploited without consequence. Engineering for Arctic conditions must address not just physical survival, but psychological well-being. Humans isolated in extreme environments face stresses that no amount of structural engineering can solve, requiring design approaches that support mental health and social cohesion. The polar night creates psychological challenges that surprised early Arctic explorers and researchers. Prolonged darkness disrupts circadian rhythms, potentially triggering seasonal affective disorder, sleep disturbances, and depression. Modern Arctic facilities engineer lighting solutions that go beyond simple illumination. Full-spectrum lighting that mimics natural daylight is increasingly standard in Arctic workplaces and living spaces. Some facilities use lighting systems that simulate daily sunrise and sunset cycles even during polar night, helping maintain circadian rhythms. These systems adjust color temperature and intensity throughout the day, providing morning blue shifted light that promotes alertness and evening warm-toned light that encourages restfulness. Window design balances insulation requirements with psychological needs for natural light and outside views. Even when outside is dark and cold, windows provide psychological connection to the environment that windowless spaces cannot. Some Arctic buildings use additional windows beyond what thermal efficiency would dictate, accepting higher heating costs in exchange for improved occupant well-being. Social space design is critical in isolated Arctic facilities. Communal areas for dining, recreation, and casual interaction prevent the isolation and cabin fever that can develop when people retreat to private spaces. Antarctic research stations, hosting people for months-long winter deployments, include gyms, libraries, movie theaters, and recreation rooms as essential infrastructure, not luxuries. Privacy also matters. While communal spaces are important, private quarters where people can retreat allow the alone time necessary for mental health. The balance between private and social space requires careful architectural planning. Communication systems that maintain contact with outside world are psychologically critical. Modern satellite internet allows Arctic residents to video call family, access entertainment, and maintain connection to life beyond the ice. This connectivity was impossible a generation ago, when isolation was far more absolute. Some Arctic facilities employ psychologists or mental health professionals as part of their core staff, recognizing that psychological challenges are predictable aspects of Arctic life requiring professional support. The engineering lesson is that successful Arctic habitation requires designing for humans as psychological beings, not just biological organisms requiring warmth, food, and air. Engineering for extreme cold requires specialized knowledge that isn't part of standard engineering curricula. Universities and specialized training centers have developed programs specifically addressing Arctic and Antarctic engineering challenges. The University of Alaska Fairbanks operates one of the world's premier Arctic engineering research and education programs. Students learn not just theoretical principles, but practical skills working with materials and equipment in actual extreme cold conditions. Training includes understanding how materials behave at temperatures from -40 to -100 degrees Fahrenheit. Students test steel samples at various temperatures, observe concrete curing in cold conditions, and work with lubricants and fluids that behave completely differently than in temperate environments. Practical skills training includes operating equipment in extreme cold, learning the procedures for cold-starting engines, maintaining hydraulic systems when fluid thickens, and performing repairs while wearing heavy gloves that limit dexterity. Safety training is extensive. Students learn to recognize early symptoms of frostbite and hypothermia, understand how quickly exposed skin freezes at various temperatures, and practice emergency procedures for equipment failure in remote locations. Norway's universities offer specialized programs in Arctic marine engineering, focusing on ship design, offshore platform engineering, and ice mechanics. Students learn the physics of ice loads, design principles for ice-resistant structures, and navigation in ice-covered waters. Russia maintains several institutions specializing in permafrost engineering, training civil engineers specifically in foundation design, building construction, and infrastructure development for frozen ground conditions. This specialized education has no real equivalent in countries without extensive permafrost regions. Military services operate their own Arctic training facilities. The U.S. Army's Northern Warfare Training Center in Alaska teaches cold weather operations, survival, and equipment maintenance. Similar facilities exist in Norway, Russia, and Canada. Industry-specific training addresses particular sectors. Oil and gas companies train engineers in Arctic drilling techniques, pipeline design for permafrost regions, and offshore platform operations in ice. Mining companies provide training in Arctic mine development and operation. The The common thread across all these programs is recognition that engineering expertise developed in temperate climates doesn't transfer directly to extreme cold environments. Successful Arctic engineering requires specific knowledge, specialized training, and often direct experience working in the conditions. Arctic engineering projects cost multiples of what similar projects would cost in temperate regions. Understanding these economics is crucial to comprehending why Arctic development proceeds slowly despite vast resource potential. Construction costs in remote Arctic locations can run 3 to 5 times higher than in accessible temperate regions. Labor costs more. Workers require higher wages to work in extreme conditions and remote locations. Housing and feeding workers in remote camps adds substantial expense. Materials cost more because of transportation. Everything must be shipped, often thousands of miles, sometimes using specialized ice-capable vessels or aircraft when standard shipping isn't possible. A bag of concrete that costs $5 in Seattle might cost $50 in a remote Alaska location after transportation. The construction season is compressed. In many Arctic locations, heavy construction can only occur during summer months, perhaps 3 to 4 months annually. Projects that could be built in 1 year elsewhere might require 3 to 4 years in the Arctic, with crews mobilizing for brief construction seasons then demobilizing for winter. Energy costs are enormous. Heating buildings and operating equipment in extreme cold requires fuel quantities unimaginable in temperate climates. Remote locations often depend on diesel generators for power, with fuel transported in at great expense. Energy can represent 30 to 40% of operating costs for Arctic facilities. Maintenance costs are higher. Equipment wears faster in extreme cold. Buildings require more frequent repairs. Infrastructure like roads and runways need constant attention to prevent damage from freeze-thaw cycles and permafrost changes. These economics create a high threshold for project viability. Only very valuable resources, major oil and gas fields, high-grade mineral deposits, or facilities with strategic military value justify the costs of Arctic development. Resource extraction projects must generate enough revenue not just to cover extraction costs, but to amortize the enormous infrastructure investments required. A mine in temperate regions might be economically viable with moderate ore grades. The same ore body in the Arctic might be unprofitable because infrastructure costs consume too much of the revenue. Government subsidies and strategic priorities sometimes override pure economic calculations. Russia maintains Arctic cities and military bases partly for strategic territorial control, accepting economic costs that private enterprise wouldn't. Research stations in Antarctica operate with government funding because the scientific and strategic value outweighs economic returns. The economics are changing as technology improves and climate change alters Arctic conditions. Extended ice-free seasons reduce shipping costs. Better equipment operates more efficiently in cold. But Arctic development will likely always carry significant cost premiums over temperate alternatives. Before modern engineering reached the Arctic, indigenous peoples had already solved the fundamental problems of survival and flourishing in extreme cold. Their solutions, developed over thousands of years, offer lessons that modern engineering is only beginning to fully appreciate. Inuit, Sami, Nenets, and other Arctic indigenous peoples developed clothing systems that remain unsurpassed for extreme cold. Multiple layers of animal fur and hide create insulation through trapped air while allowing moisture from body perspiration to escape. Modern synthetic materials struggle to match this combination of warmth and breathability. The traditional parka design uses a large hood that creates a warm airspace around the face, while protecting against wind. Modern extreme cold weather clothing has essentially adopted this design, validating what indigenous peoples understood through empirical experience. Footwear technology developed by Arctic peoples addresses problems that modern materials science has difficulty solving. Boots made from seal or caribou hide are waterproof yet breathable. They remain flexible in extreme cold, unlike rubber or most synthetic materials. Inner insulation from fur or woven grass provides warmth while allowing moisture to escape. Transportation technologies, sleds, snowshoes, kayaks, represent sophisticated engineering using locally available materials. Sleds are designed with flexibility that allows them to traverse rough ice without breaking. The runners, often made from bone, antler, or special wood, can be iced to reduce friction. Modern expeditions still use sleds based fundamentally on these indigenous designs. Housing technologies varied by region, but shared common principles. The igloo is the most famous, but other structures included semi-underground dwellings that used earth for insulation, tent structures with multiple layers for air trapping, and permanent buildings using turf, stone, and driftwood. These structures succeeded because they worked with the environment rather than fighting it. They used materials available locally. They could be constructed without specialized tools. They provided adequate shelter with minimal energy input for heating. Food preservation technologies allowed storing fish and game through long winters. Techniques included freezing, drying, and fermenting, methods that prevented spoilage without modern refrigeration or canning. The engineering understanding of how different preservation methods affected food safety and nutrition was sophisticated. Modern Arctic engineering increasingly consults indigenous knowledge holders. Traditional understanding of ice conditions, weather patterns, animal behavior, and environmental changes provides insights that scientific instruments and models can miss. Indigenous peoples notice subtle environmental changes years before scientific monitoring detects them. Some modern Arctic buildings incorporate traditional principles alongside contemporary technology. Structures might use modern materials, but employ traditional design elements like entrance configurations that prevent cold air infiltration or window positioning based on traditional knowledge of sun patterns and wind directions. Recognition is growing that indigenous Arctic engineering wasn't primitive technology awaiting modern improvement. It was highly developed, deeply sophisticated understanding of survival in extreme environments that modern engineering can learn from rather than simply replace. The Arctic of the coming decades will be fundamentally different from the Arctic that drove engineering developments of the past century. Climate change, technological advancement, and shifting geopolitical priorities are converging to create a future Arctic that requires entirely new engineering approaches. Permafrost, which has provided stable foundations for Arctic construction for generations, is thawing across vast regions. Future engineering must design for unstable or variable ground conditions, rather than the reliable frozen base that previous generations assumed would last indefinitely. Some engineering approaches involve accepting permafrost loss and designing accordingly. Foundations that don't depend on frozen ground, adjustable systems that can be releveled as ground settles, and even floating structures that rise and fall with ground conditions are all being explored. Other approaches attempt to preserve permafrost artificially through active cooling systems. But this creates dependency on continuous energy input and maintenance that raises questions about long-term sustainability and cost. Extended ice-free seasons in Arctic seas are transforming maritime engineering requirements. Ships will need less ice-breaking capability, but more capacity for open water navigation and storm conditions. Port facilities designed for ice-covered harbors must adapt to open water with wave action. The paradox is that climate change makes some Arctic regions more accessible, while creating new instabilities and challenges. What appears to be an opportunity, easier access, reduced ice, longer construction seasons, comes paired with uncertainties about permafrost stability, changing storm patterns, and ecosystem disruptions. Arctic cities of the future will likely need to be far more adaptable than those built in the 20th century. Rather than designing for stable conditions, they'll need to accommodate changing climate, variable ground conditions, and uncertainty about what conditions will prevail in 30 or 50 years. Renewable energy systems will become more viable as Arctic conditions shift. Solar power becomes more practical with reduced ice cover and longer daylight periods during summer. Wind energy potential may increase with changing atmospheric patterns. Hydroelectric power from glacial meltwater could expand, though glacial retreat creates its own complications. Transportation infrastructure faces fundamental questions. Permanent roads built on permafrost may become impractical in regions where permafrost is degrading. Alternatives might include more reliance on air transport, seasonal ice roads when conditions permit, or amphibious vehicles that can operate on land, ice, or water. The Arctic may see development of year-round settlements in regions currently accessible only seasonally. Extended ice-free periods around Greenland and northern Canada could enable ports and communities where none exist today. But development will likely be more selective than the expansive Arctic settlement visions of the mid-20th century. The enormous costs of Arctic construction, environmental concerns, and alternatives available in more temperate regions mean that only locations with exceptional resource value or strategic importance will likely see major development. Indigenous communities, who have inhabited Arctic regions longest, will play increasing roles in determining how development proceeds. Their land rights, traditional territories, and accumulated environmental knowledge give them both legal standing and practical expertise that development projects must engage with. The engineering challenge of the future Arctic isn't primarily technical. It's integrating technical capability with environmental sustainability, economic viability, indigenous rights, international cooperation, and adaptation to rapidly changing conditions that make past experience an unreliable guide to future needs. The story of how nations conquer ice is ultimately a story about human ambition confronting absolute limits. The Arctic and Antarctic don't bend easily to human will. They don't compromise. They impose engineering requirements that are technically possible but economically punishing and environmentally consequential. Yet people live there. Cities exist where survival should be impossible. Industry extracts resources from frozen ground. Research stations occupy the coldest places on Earth. This isn't primarily about technological capability, it's about determination. The engineering makes it possible, but human will makes it happen. The indigenous peoples who first inhabited Arctic regions understood something that modern engineering is relearning. You can't defeat the ice. You can only adapt to it, work with it, and respect its power. The most successful modern Arctic engineering follows this principle, using sophisticated technology not to overcome the cold, but to accommodate it. Russia's massive investment in Arctic cities and infrastructure represents a determination to maintain territorial control and resource access regardless of cost. These cities exist because a nation decided they should exist, marshaling the engineering capability and economic resources to make it happen. American military installations scattered across the Arctic during the Cold War made similar statements. These bases weren't economically rational. They were strategic assertions that national security justified any cost. Many have been abandoned as